Welcome to Lecture 10. This week we're going to move on to Chapter 6 and we'll talk about all of Chapter 6. Volumes using cross sections, volumes using cylindrical shells or the shell method, arc length and areas of surfaces of revolution. First, let's talk about volumes using cross sections. Let's suppose we have some sort of three-dimensional object like this, in which we know the cross-sectional area. What is the volume of this object? Well, what we can do is we can slice this object like we would slice a loaf of bread. Here we are. More precisely, we're going to use a partition to partition our closed interval from A to B into lots of little sub-intervals. And then on each one of these little sub-intervals, we're going to approximate that part of the solid object by a type of cylinder, an irregular cylinder. Here we are, like this. We're going to calculate the volume of this, and then we'll take the limit as n tends to infinity, and we'll obtain a formula for the volume of the object that we started with. So what is the volume of one of these little pieces? Well, we know its width. Its width is the difference between xk minus 1 and xk. We'll call that delta xk. And we know the cross-sectional area because we started by knowing the cross-sectional area of our solid object. So the volume of one of these pieces is going to be A of xk multiplied by delta xk. Add them all together, we have our Riemann sum. The sum from k is equal to 1 to n of A xk delta xk. And then we want to take the limit as n tends to infinity. When we take the limit, delta xk changes to dx. And when we take the limit, the sum will change to an integral. So when we take the limit, we'll get the integral from a to b, ax dx. And that's our formula. You don't necessarily need to know how to derive this formula, but you need to know how to use a formula like this. The textbook suggests that we solve the following problems like this. Step 1, sketch the solid and a typical cross-section. Step 2, find a formula for ax. Step 3, find the limits of integration, a and b in the previous picture. And then step 4, do the integration. Let's do a couple of examples. A 3 meters tall pyramid has a square 3 meters by 3 meters base, as shown in this picture. The cross section, x meters from the vertex at the top, is an x meter by x meter square. Find the volume of the pyramid. Okay, we have our picture and we have our formula in the yellow box at the top. So we need to find two things. We need to find the cross-sectional area AX, and we need to find the limits of integration. And then after we've done those, it's going to be an easy problem. I'm going to turn this pyramid on its side because just turning it around doesn't change its volume. And I'm drawing it so that its central axis is on the x-axis. The question said that if we're x meters away from the vertex, away from what was the top of the pyramid, then the cross-section is going to be an x meter by x meter square, which I've drawn in green here. What is the area of a square of side x? The area is x squared. What are the limits of integration? Now look at the picture. What is the smallest possible x? The smallest possible x here is x equal to 0. And what is the biggest possible x inside the pyramid? The biggest possible x is going to be x equal to 3. So we're going to be integrating for x between 0 and 3. And now we've done the hardest part of the question done. Find the formula for ax, x squared. Find the limits of integration, x is between 0 and 3. We've done all of the hard work. All that's left is to calculate the integral. The integral from 0 to 3, x squared dx, that's just 9. So the volume of this pyramid is 9 cubic meters. Let's do another example. A curved wedge is cut from a cylinder of radius 3 by 2 planes. Here's a picture of my cylinder. The first plane is perpendicular to the axis of the cylinder. And then we have another plane which is crossing the first plane with an angle of 45 degrees at the center of the cylinder. So imagine cutting our plane with a knife which moves along, cutting our cylinder with a knife which moves along these planes. We're going to obtain this object which we're calling a wedge. And then the question says, find the volume of the wedge. Okay, so here's a picture of the wedge. Let me rotate this around so we can see what we're doing. We need to find the cross-sectional area, AX, and we need to find the limits of integration. Where's the cross-sectional area here? It could be this green rectangle. Let's take a top view. Because we started with a cylinder of radius 3, this curve at the bottom is going to be x squared plus y squared is equal to 3 squared. That's the equation of a circle of radius 3. So that means if we look down from the top, if we think of this curve as y as a function of x, the top half is going to be y is the square root of 9 minus x squared. That's just rearranging the first formula. And the bottom half would be y is equal to minus square root of 9 minus x squared. So what is the width of the green rectangle? What is this distance? Well, root 9 minus x squared on the top, minus root 9 minus x squared on the bottom. The width of our rectangle must be 2 times root 9 minus x squared. And what is the height of our green rectangle? Let's have a look at the side view of our wedge. I have a distance x. I have an angle 45 degrees. So what is the height of this green rectangle? Of course, the height must also be x because the angle is 45 degrees. So the area of our green rectangle is 2x square root of 9 minus x squared. And what are our limits of integration? What's the smallest possible x? X is 0. What is the biggest possible value of x here? The biggest possible value of x is 3. So to summarize, the cross-sectional area, AX is 2x root 9 minus x squared, and we want to integrate between 0 and 3. So the answer to this question is going to be the value of the integral from 0 to 3, 2x square root of 9 minus x squared dx. We've done almost all of the problem now. All that's left is to calculate this integral to get a number. For an integral like this, we want to do a substitution. Let u be 9 minus x squared, and then du is minus 2x dx. Make the substitution. We have the integral of minus u to the power of a half dx. Now I'm doing something a little bit different here. I'm keeping the limits of integration as limits with respect to x. So it's going to be the integral from x is 0 to x equal to 3 of minus u to the power half d. An antiderivative of u to the power of a half is 2/3 u to the power of 3 over 2. Substitute in 9 minus x squared. We want to calculate minus 2/3, 9 minus x squared, all to the power of 3 over 2 at x equal to 3 and x equal to 0. And when we do that, we get the answer 18. But this last bit was the easy bit. You know how to calculate integrals like this. The important part of this problem was drawing the picture and understanding what is the cross-sectional area and what are the limits of integration. Let's move on to the next idea. My next idea is solids of revolution. And the first thing we'll look at is the disk method. Let's suppose we have a region in the xy plane, like this one, say, and then let's suppose we hold the x-axis and we rotate this around in three-dimensional space to obtain a three-dimensional object like this. What is the volume of this three-dimensional object? A solid like this, an object like this, generated by rotating a plane region about a line in the plane, is called a solid of revolution. And we have our formula from before. The volume is the integral from a to b, cross-sectional area ax dx. But what is our cross-sectional area here? Our cross-sectional area is a circle. And what is the area of a circle of radius r? Pi r squared. So our formula for the volume of this three-dimensional object is the integral from a to b, pi r squared dx. Okay, I'm going to take this and I'm going to put this at the top. First example, the region between the curve y is equal to the square root of x in the x-axis for x between 0 and 4 is rotated about the x-axis to generate a solid. Find its volume. The formula that we are going to use is the integral from a to b, pi r squared dx. What is a, what is b, and what is r? Well, r is, we can see from the first picture. R is the length of this line. The top is at root x, and the bottom is at 0. Root x minus 0 is root x. So capital R is going to be the square root of x. What are the limits of integration? The smallest value of x, 0, and the biggest value of x, 4. So we want to integrate from 0 to 4, pi multiplied by root x squared. And I'll leave it for you to check that this means the volume of this three-dimensional object is 8 pi. Let's do another one. Find the volume of a sphere of radius A. And again, we're going to be using the formula in the yellow box at the top. How can we generate a sphere? We could take a semicircle and then we could rotate it around the x-axis to generate this sphere. So because we want a sphere of radius A, we're going to start with y is equal to the square root of a squared minus x squared. That's the formula for a semicircle of radius A. We're going to rotate this about the x-axis. So what do we have? What are our limits of integration? The smallest value of x is here, minus a, and the biggest value of x is a. So we're going to be integrating between minus a and a. And what is our radius? Well, we know the formula at the top. We know the bottom is y equal to 0. So the radius is going to be the square root of a squared minus x squared. The volume of the sphere is going to be the integral from minus a to a, pi r squared, or integral from minus a to a, pi, multiplied by root a squared minus x squared, all squared. And when we calculate this integral, we get 4/3 pi a cubed, which some of you will already know is the formula for the volume of a sphere of radius a. Time for another example. Find the volume of the solid generated by revolving the region bounded by y is equal to the square root of x and the lines y equal to 1 and x equal to 4 about the line y equal to 1. Now this is different. This time we're not rotating around the x-axis. This time we're rotating around the line y equal to 1. But still, the idea is the same. We have our formula in the yellow box at the top. We need to know two things. We need to know the limits of integration, and we need to know the radius of our cross-sectional area. So we look at the picture. We look at the picture A. What is the smallest value of x? What is the biggest value of x? You zoom in. Smallest value of x here is x is 1. Biggest value of x in our region is x is 4. So we're going to be integrating between 1 and 4. And what is our radius? What is the length of this pink line? Well, we have square root of x at the top, and we have 1 at the bottom. So the length of this pink line is going to be root x minus 1. And that's it. That's all we need. We have our radius. We have our limits of integration. We'll just calculate the integral. We're going to be integrating from 1 to 4, pi r squared. So that's pi root x minus 1 all squared. And after that, I'm going to leave it for you. Your book says it's 7 pi over 6, but the last part I think is not interesting for us. As soon as we get the radius, we get the limits of integration, the rest of the problem is easy. So far, we've been rotating about the x-axis or rotating around lines which are parallel to the x-axis. But what if instead we rotated about a vertical line? Let's say we rotated about the y-axis. Well, the idea is exactly the same. It's going to be an integral of the cross-sectional area. Now it's going to be a function of y and then dy if we're rotating around the vertical line. Or for the disk method, the integral from from C to D, pi r squared dy. For example, find the volume of the solid generated by revolving the region between the y-axis and the curve x is equal to 2 over y for y between 1 and 4 about the y-axis. Okay, formulas in the yellow box at the top. We need to know the limits of integration. That's easy. The question tells us that y is between 1 and 4. And we need to know the radius r of y. The right-hand end of this pink line is at x equal to 2 over y, and the left-hand end is at x equal to 0. So we do right-hand end minus left-hand end. 2 over y minus 0. The radius is going to be 2 over y minus 0, or 2 over y. So the volume of this three-dimensional object is going to be the integral from 1 to 4 pi r squared pi 2 over y all squared dy. And I'm not even going to bother finishing this question. I'm just saying equal to dot dot dot. I'm sure you can finish this if you wanted to. Let's go to another example. Find the volume of the solid generated by revolving the region between the parabola x is equal to y squared plus 1 and the line x equal to 3 about the line x equal to 3. Okay, so we need the limits of integration. We need the bottom. What is the smallest possible value of y? Well, we can calculate that by starting with y squared plus 1 is equal to 3. Rearranging that, we find root 2 and minus root 2. So the smallest possible value of y must be minus root 2, and the biggest possible value of y must be the square root of 2. Okay, so that's our limits, root 2 at the top, minus root 2 at the bottom. The second thing we need is the radius. It's going to be right-hand end minus left-hand end. So what's the right-hand end? The right-hand end is 3. What is the left end? The left end is y squared plus 1. So the radius is going to be 3 minus y squared plus 1. And that simplifies to 2 minus y squared. And that goes in here. And then we've done the hard work. The volume of our three-dimensional object is going to be the integral from minus root 2 to root 2 pi 2 minus y squared all squared dy. And again, I'm not going to finish this question. I've lost interest now. I'll leave the rest of this problem for you to finish. For problems like this, you need to find the limits of integration, you need to find the radius, and then after that, I think it becomes easy. Let's move on to our next idea. Now I want to talk about solids of revolution, the washer method. The area of a disk or a circle is pi r squared. An area of a washer or an annulus like this with an outer radius capital R and inner radius minus r, or its area of a circle minus area of a circle. So pi capital R squared minus pi small r squared. And we're going to use that for things like this. Let's suppose we take the region on the left and we rotate it around the x-axis. we would generate an object like the picture on the right. And then the cross-sectional area will not be a circle, the cross-sectional area will be a washer. So the volume of the object on the right is going to be the integral from a to b, ax dx, or in terms of area of a washer, integral from a to b pi, and then open bracket, capital R squared minus small r squared. To answer questions like this, we need to find the limits of integration, we need to find the outer radius capital R, and we need to find the inner radius small r. Okay, let's do an example. I've put our formula in the yellow box at the top, and I want to answer the question, the region bounded by the curve y is equal to x squared plus 1, and the line y is equal to minus x plus 3 is revolved about the x-axis to generate a solid. Find the volume of the solid. Now, from this picture, we can gain a lot of information. It tells us that these two curves intersect when x is 2 and when x is 1. So our interval of integration is going to be between minus 2 and 1. Okay, minus 2 there, 1 up there. We need to know the outer radius and the inner radius. What is the easiest way to find which is capital R and which is smallest r? Because volume is always positive. If you get it wrong, you'll end up with a negative number, and then you go back and you fix your answer. Capital R is always the bigger one, little I is always the smaller one. If you get it wrong, you'll end up with a negative volume, and then you go back and you erase your answer, change it around, and then you'll write down the correct answer. So we have our two functions, minus x plus 3 and x squared plus 1. Which one of these is bigger? Well, let's have a look in the middle. Let's use x equal to 0 because 0 is an easy number. The first one becomes 0 plus 3, and the bottom one becomes 0 plus 1. So now I know minus x plus 3 is the bigger one, and x squared plus 1 is the smaller one. And that's all we need. We have our limits of integration, we have capital R, we have small r. All that's left is to put these into the formula. So it's integral from minus 2 to 1, pi, open bracket, capital R squared. For us, that's minus x plus 3 squared, minus small r squared. For us, that's x squared plus 1 squared. And then it's an easy integration to get the answer 117 pi over 5. If you get big R and small r mixed up, then you'll end up with a minus sign here, and then you'll know that you've made a small mistake. How did we get 8? So it comes from 3 squared is 9 minus 1 squared. 9 minus 1 is 8. That was rotating about the x-axis, but of course we could rotate around the y-axis as well if we wanted to. Nothing changes. All we're doing is everywhere there was an x in the previous formula, we'll just replace it by y. Other than that, the idea is exactly the same. Let's do one example. The region bounded by the parabola y is equal to x squared and the line y is equal to 2x in the first quadrant, that means x is positive, y is positive, is revolved about the y-axis to generate a solid. Find the volume of the solid. Because we're revolving about the y-axis, we want to integrate dy. And then for the limits of integration, we want the smallest value of y and the biggest value of y. In this picture, the smallest value of y is 0 and the biggest value of y is 4. So we could write 0 and 4. Then we need to find capital R of y and small r of y. And here the question's been a little bit sneaky because it told us y as a function of x. But we don't want that. We want the other way around. We want x is square root of y, and we want x is equal to y over 2. Which one of these is the biggest one? Let's choose an easy number. This time let's choose y is equal to 1 because 1 is an easy number. If y is equal to 1, then I have square root of 1 and I have 1 over 2. Which one of these numbers is the bigger one? Which one is the smaller one? Square root of 1 is the bigger one, a half is the smaller one. So capital R must be square root of y and small r must be y over 2. And that is the hardest part of the question done. All that's left is to put this information into the formula and calculate its answer. Integral from 0 to 4, pi, capital R squared, that's root y squared, minus small r squared, that's y over 2 squared. And as before, equal to dot, 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 because I got bored. I'll leave the rest of this for you to do. If you used the law correctly, but the end result was wrong, you would get partial marks, depending on how correct or how wrong your answer is. Let's move on to the next idea. Volumes losing cylindrical shells. I'm going to talk about this section, and then after this, we'll take a 10-minute break. Yes, this chapter is included in the second midterm exam, and there is at least one question on the exam from topics in today's lesson. For the disc and the washer method, we were cutting our three-dimensional object like we would cut a loaf of bread, writing down a Riemann sum and then taking the limit of the Riemann sums to get our formula. But there's another way we might cut a solid of revolution. We could cut it using circular cookie cutters or pie cutters. Let's suppose we have some three-dimensional object like this, and then let's suppose we use these circular cutters to cut it along these orange lines. Each one of these pieces we can approximate using this type of shape, which is I'm calling a shell. You just rotate this around a little bit. This is going to be our Riemann sum. We want to calculate the volume of one of these pieces, and then we'll add them together to get a Riemann sum, and then we'll take the limit. So what is the volume of something like this? Well, we can imagine that we cut this. Let's suppose we cut it down. And then let's suppose if this is made of rubber, say, we could unfold it until we end up with the picture at the bottom. Yes, I know when we unfold it like this, the volume will change very, very slightly, but that doesn't matter because we're going to be taking the limit anyway, so don't worry about that. What is the volume of this piece at the bottom? If we know its height, if we know that the width of this piece is 2 pi multiplied by the radius that we started with, because the circumference of a circle is 2 pi radius. And if we know its thickness, we multiply these three numbers together to get the volume of this object. So the volume of one of these shells is going to be approximately 2 pi times the radius multiplied by the height multiplied by the thickness. And if we add all of these shells together, we get our Riemann sum. When we take the limit of a Riemann sum, delta xk changes to dx, and sum changes to integral. So when we take the limit of the Riemann sums, we'll get our formula. Volume is the integral from a to b, 2 pi, shell radius, shell height, dx. Now, you don't need to learn how I created this formula. You just need to know how to use this formula. From your book, the volume of the solid generated by revolving the region between the x-axis and the graph of a continuous function, y is equal to f of x, which is greater than or equal to 0. For L less than or equal to a, less than or equal to x, less than or equal to b, about a vertical line x equal to L is the formula. Volume is the integral from a to b, 2 pi, shell radius, shell height, dx. So this is our formula. I'm going to put this in the yellow box at the top. And we're going to use that to solve this example. The region bounded by the curve y is equal to the square root of x, the x-axis and the line x equal to 4 is revolved about the y-axis to generate a solid. Find the volume of the solid. We zoom in on our region. We need to find the shell radius and we need to find the shell height. And the way that I like to think about this is I like to think that we're going to use a giant capital H. One of the vertical parts of this capital H should go on the axis of revolution. The other vertical line becomes the shell height. And then if we join these two together, we get the shell radius. So what can we say? First of all, what are the limits of integration, the a and the b here? Smallest value of x in this region, biggest value of x in this region, those are 0 and 4. What is the shell height? Well, square root of x at the top, 0 at the bottom. The shell height must be root x. And what is the shell radius? I have x on the right hand side and I have 0 on the left. The shell radius must be x. Let me repeat that. X is between 0 and 4. The shell height is root x, and the shell radius is x. And that's the hardest part of the question done. If you can understand that, if you can do that, then you've done 90% of the problem already. All that's left is going to be an easy integration to get our final answer. Volume is the integral from a to b, 2 pi, shell radius, shell height, dx. So that's integral from 0 to 4, 2 pi x root x dx. And that's easy, right? When we calculate this integral, you could check that we get 128 pi over 5. Let's do another one. But before we do another one, let me just remark, when we do the shell method, it doesn't really matter if you get the shell radius and the shell height mixed up, because you're just going to be multiplying these two numbers together. So you'll still end up with the correct final answer, and at most, you're only going to lose a few points in the exam. So don't worry too much if you get shell radius and shell height confused. Okay, question from the chat. We have x and root x. How do we get rid of the x? We don't. We have x to the power 1, and we have x to the power of a half. The green x is x to the power 1, and root x is x to the power of a half. And of course, 1 plus a half is 3 over 2. So that's why I have x to the power 3 over 2 just here. Next question from the chat. Will the question tell us what method to use, or do we have to figure that out from the graph? You could be given each type of question. A question might be written of the way, use the shell method too. If the question says that, then you have to use the shell method. If it doesn't tell you that, then you can use any method that you want. And if you're not told which method to use, it's probably equally easy to use either method. Will you give us at least one question that's likely to come in the exam, like the last exam? No. But let's do another example of this shell method. This is exercise 1 on page 348 of your textbook. The region bounded by the curve y is equal to 1 plus x squared over 4, and the x-axis for x between 0 and 2 is revolved about the y-axis to generate a solid. Find the volume of the solid. The first thing I like to do is I like to draw my capital H. One of the vertical lines goes on the axis of revolution. A parallel line is the shell height, and then join them together, we get the shell radius. What can we read off from here? Well, first of all, the limits of integration. The smallest x and the biggest x, 0 and 2. What is the shell height? Well, we know at the bottom it's 0, and we know at the top it's 1 plus x squared over 4. So the shell height must be 1 plus x squared over 4. What is the shell radius? That's x on the right, 0 on the left. The shell radius must be x. And that's the hardest part done. If you could understand that much, then you could solve a method using the shell method, a question using the shell method. Because the rest of this question is just sticking these things into the formula and then calculating the integral, which I'm not going to do. Equal to dot, dot, dot. I'm not going to spend time in this lesson calculating this. Instead, let's do another example. The region shown below is revolved about the y-axis to generate a solid. Find the volume of the solid. So step one is to draw my capital H. And then I want to read off the information from the graph. I can see that x is between 0 and 2 here. The shell height, or the top of the shell, is at 2 minus x squared over 4, and the bottom is at y equal to 0. So the shell height must be 2 minus x squared over 4. Shell radius, I can see, must be x. So the volume of the solid must be integral from 0 to 2 pi x 2 minus x squared over 4 dx. And that's equal to whatever it is. You can finish this for me now. So that's the shell method when we rotate about a vertical line. Integral from a to b, 2 pi, shell radius, shell height, dx. We could also rotate about a horizontal line. And this time we also have the shell method, but we're rotating everything, so we're going to be rotating the capital H. And what is the difference in the formula? The only difference is we're going to be integrating with respect to y instead of with respect to x. It's still integral from a to b, 2 pi, shell radius, shell height, dy. I'm going to do an example of a shell method with rotating about a horizontal line. So in the next example, I'm going to be writing my capital H like this. The region bounded by the curve y is equal to the square root of x, the x-axis and the line x equal to 4, is revolved about the x-axis to generate a solid. Find the volume of the solid. I need to draw my large capital H, and this time, because we have a horizontal axis of revolution, I'm going to be drawing an H like this. Always one side of the capital H goes on the axis of revolution. The shell height is always parallel to the axis of revolution, and then the shell radius joins them together. Now that we've drawn our large capital H, we can read off the information. Now, remember, we're integrating with respect to y now. So for the limits, we want the smallest y and the biggest y. Biggest y must be 2, because if x is 4, then y is 2, and the smallest y must be 0. So we're integrating between 0 and 2. The shell height, okay, so on the right-hand side, it's 4. And on the left-hand side, it's y squared. Right minus left will give us 4 minus y squared. And the shell radius, the top is at y and the bottom is at 0. Y minus 0 is y. The shell radius must be y. Question, how is y square? So I'm guessing I think you're talking about the shell radius. So let me go back to talking about that. I want to work out the length of this orange line, this shell height. On the right-hand line is x is equal to 4. On the left-hand line, it's x is equal to y squared. Remember, if we're integrating with respect to dy, then we want to get functions of y. So we want to get rid of all the x's. So it's right-hand end, or 4, minus left-hand end. The left-hand end is at y squared. So that's why it's 4 minus y squared. And then we've done 90%, 99% of the problem, because the rest of the problem is just going to be an easy integral. Integral from 0 to 2 pi, y, 4 minus y squared dy is equal to ... whatever this is. The region bounded by the curve y is equal to the square root of x. The x-axis in the line y equal to 4, that's the same so far, but this time we're revolving about the line y is equal to -1 to generate a solid. Find the volume of the solid. So if I just quickly flick back to the previous picture, previous example we had axis of revolution on the x-axis, but now we have axis of revolution on the line y is equal to -1. What's changed? Well, the limits of integration are going to be the same because the blue region hasn't changed. The shell height is going to be the same because that hasn't changed. But we can see from this picture that the shell radius is different now. The shell radius is going to be bigger than just y. So let's look at that. At the top, I have y, and at the bottom, I have -1. I want to do top minus bottom. So I want to do y minus -1. The shell radius now is going to be y plus 1. So now the volume is going to be integral from 0 to 2 pi, integral from 0 to 2 pi, y plus 1, 4 minus y squared dy. Most of this is the same as the previous example, but we have a different shell radius. Instead of just y, we have y plus 1. Now let me ask you. Looking at this picture, I've drawn the axis of revolution, I've drawn the shell height and the shell radius, and I'm asking you for you to tell me which one of these is correct. 1, 2, 3, or 4. If you click the circular item at the bottom, which looks a little bit like a bar graph, you should be able to hide and show your questions. And we have an even split between 1, 2, and 3. First of all, shell height is the orange line, because shell height is always parallel to the axis of revolution. On the left-hand end, I have 0, and on the right-hand end, it's 12 y squared minus y cubed. So the shell height is going to be 12 y squared minus y cubed. The shell radius, I'm drawing in green in these pictures. This is the shell radius. Y at the top, 0 at the bottom, the shell radius is y. The correct answer was 3. Let's do another one. I have 4 of these problems, by the way. This is problem 2. I think there's a typo here. This should be cubed. Five correct answers. The correct answer was number 1. Now let's do another one. Now the axis of revolution is x is equal to -2. This time the correct answer is number 3. This is the same region as in the previous question. The shell height is the same, still 8 minus x cubed. But what's different here is the shell radius, because I have x on the right-hand side and I have -2 on the left-hand side. So the length of this green line is going to be x minus -2 or x plus 2. Final question before we take a break. Which one of these is correct? Well done to all of those of you who clicked number 2. Number 2 was the correct answer. Now we're going to take a 10-minute break and we're going to continue at 20 past. And now let's continue. Section 6.3 is about arc length. What is the length of this curve? Just as I've done in the previous sections, I'm going to start by showing you how we derive the formula, and then I'm going to show you how we use the formula. How could we approximate the length of this shape? We could approximate it with some straight lines like this. We're going to calculate the length of this set of red lines, and then we're going to take the limit as n tends to infinity to change a Riemann sum into an integral. What is the length of one of these things? Well, on this red piece, for example, x changes delta xk and y changes delta yk. So of course, by Pythagoras, the length of this piece is the square root of delta xk squared plus delta yk squared. Add them all together, we have our Riemann sum, the sum from 1 to n of the square root of delta xk squared plus delta yk squared. Take the limit of the Riemann sums, sum changes to integral, delta changes to d. The length of this blue curve is the integral from a to b, the square root of dx squared plus dy squared. Okay, so the length of this blue curve is the integral from a to b, square root of dx squared plus dy squared. But what is the square root of dx squared plus dy squared? Think of it like this. I could factor out dx squared to write dx squared multiplied by 1 plus dy squared divided by dx squared. And then instead of dy squared over dx squared, I want to think of that as dy dx all squared. The dy squared I can take outside of the square root, and it just becomes dx. So square root of dx squared plus dy squared is the same as square root of 1 plus dy dx all squared dx. And that gives us our formula. From where we get right side, which bit are you asking about? Okay, so I'm starting with this term in green. We can forget about the square root. I have a dx squared and a dy squared. I could factor out a dx squared. If we multiply dx squared by 1, we get dx squared, and multiply dx squared by dy squared dx squared, we get dy squared. So that's the first equal sign. Now I have a dy squared and a dx squared. So that's a dy squared on the top, dx squared on the bottom. Take the factor of squared outside the bracket. Dy squared over dx squared is the same as dy over 1 dy over 1 dx all squared. And then that gives us our definition. So as I said in the previous sections, it doesn't matter too much if you don't understand where the formula comes from, because your exam questions, if you're given a question like this, will all be about using the formula. So You can ignore the previous few slides if you want to and start here. If y prime is continuous on the closed interval from a to b, and I'm going to show you that later that this is important, we need to have that f prime is continuous, then the length of the curve y is equal to f of x from x is equal to a to x is equal to b is given by this formula. The length is the integral from a to b, square root of 1 plus dy dx squared dx. And this is our formula, so I'm going to be putting this at the top. Find the length of the graph of y is equal to 4 root 2 over 3, x to the power 3 over 2 minus 1, for x between 0 and 1. Okay, straight away we're told the limits of integration. We're told that we're going to be integrating from 0 to 1. And we're told our y. We're told y. We're going to differentiate this to get dy dx. I'm going to square it, and then I'm going to stick that into the formula. Integral from 0 to 1, square root of 1 plus dy dx squared dx. So first of all, differentiate this function. You can check this for me later. I think we get 2 root 2 x to the power of a half. Square it. We get 8x. And then put that into the formula. Integral from 0 to 1, square root of 1 plus 8x dx, which is equal to dot, dot, dot. I'm not going to spend my time finishing this. Of course, in an exam, you can't write equal to dot, dot, dot if you want all the marks, but I'm not going to spend my lecture time doing easy integrals today. And that's it. Length of a curve is all about using this formula as long as f prime is continuous. Let's do another one. Find the length of the graph of f of x is equal to x cubed over 12 plus 1 over x for x between 1 and 4. So in the picture, we're not doing the right-hand part and we're not doing the left-hand part. We're only interested in the curve between 1 and 4. Well, that tells us our limits of integration. We need to take our function, we need to differentiate it, square it, plus 1, and then take its square root. So, x cubed over 12 plus 1 over x. Differentiate this. X squared over 4 minus 1 over x squared, right? And then square it and add 1. I'll leave this for you to check later. Check that it all neatly comes down to x squared over 4 plus 1 over x squared, all squared. And then we put that into the formula that we get from the yellow box. Integral from 1 to 4, square root of 1 plus f prime squared dx. That's integral from 1 to 4, x squared over 4 plus 1 over x squared dx, which is equal to dot, dot, dot. You can finish this for me. So that was length of a curve if we integrate with respect to x. But of course, we could swap the positions of x and y and integrate with respect to y instead. So this is almost exactly the same as the previous definition. If we have a function whose first derivative is continuous on the closed intervals from c to d, then the length of the curve x is equal to g of y from x equal to c to x equal to d is given by this formula. Integral from c to d, square root of 1 plus g prime of x, all squared, dx is equal to integral from c to d, square root of 1 plus dx dy squared dy. All I've done here is I've swapped x and y in the previous formula. Instead of dy dx here and then dx on the end, it's dx dy and then dy on the end. For example, find the length of the graph y is equal to x over 2 all to the power 2 over 3 for x between 0 and 2. Now, note first, if we differentiate this with respect to x, I get 1/3 2 over x all to the power 1 over 3. And this is not defined if x is equal to 0. We can only use these length of curve formulae if f prime is continuous on our closed interval. And here we have a function which is not defined on the left end of our interval. So we can't use our first formula. We can't use length is equal to the integral from a to b, square root of 1 plus dy dx squared dx, because dy dx is not continuous. So instead, we need to use the second formula. Instead, we're going to use the formula integral from c to d, square root of 1 plus dx dy squared dy. From where do we get 1 over 2? From where does this one come? It comes from the chain rule. When we differentiate this, we get 2/3 down the front, x to the power minus 1 over 3 multiplied by d dx of x over 2. And d dx of x over 2 is 1 over 2. Okay, so let me repeat ourselves. We can only use these formulae if our derivative is continuous. We can't use the first one because dy dx is not continuous. So instead, we have to use the second formula. So I've put this in the yellow box. This is the formula we're going to use. I need dx dy, and so far I only have y is equal to a function of x. So the first thing to do is to rearrange this. Put each side to the power 3 over 2 to get y to the power 3 over 2 is x over 2, and then multiply both sides by 2. This is the same as x is equal to 2y to the power 3 over 2. Then I'm going to differentiate this with respect to y to get dx dy is 2 multiplied by 3 over 2, y to the power of a half, or 3y to the power of a half. And now there's no problem because this function is continuous for y between 0 and 1. So all that's left to do is to take this and stick it into our formula up here. The length is the integral from 0 to 1. Remember, we're integrating with respect to y, so it's y0 up to y1. Square root of 1 plus 9y dy is equal to ... whatever it is. And then we have one more section to cover. Areas of surfaces of revolution. Again, let's take the graph of some function. Let me rotate this around. And then I want to rotate this curve about the x-axis to generate a surface. And I'm doing that like this. And then my question is, what is the area of this surface? Now, this time I'm just going to tell you the formula. I'm not going to show you how to derive it. I'm just going to show you the formula, and then I'm going to show you how to use the formula. If the function f of x, which is we need to always be greater than or equal to 0, is continuously differentiable, that means we can differentiate it and we still have a continuous function on the closed interval from a to b. So that was the same as the length formula. We need f prime to be continuous. Then the area of the surface generated by revolving the graph y is equal to f of x about the x-axis is given by this formula. And I've left the length formula at the top in the yellow box because they're almost the same. The only difference is that for surface area, we have an extra 2 pi y, which is the circumference of a circle of radius y. For example, find the area of the surface generated by revolving the curve y is equal to 2 root x for x between 1 and 2 about the x-axis. Okay, so we have our formula at the top. We're told our limits of integration. We're told that x is between 1 and 2. And we have our graph, y is equal to 2 root x. So we're just going to be putting everything into the formula to get our answer. Y is 2 root x, so dy dx is 1 over root x. That is continuous between 1 and 2, no problems there. 1 plus dy dx squared. That's the same as x plus 1 over x. So the surface area is integral from 1 to 2 pi, and then y, so 2 root x, and then square root of 1 plus dy dx squared. For us, that's square root of x plus 1 divided by square root of x. They will cancel. Really, we're just doing integral of 4 pi root x plus 1. And I'll leave that for you to do. We can also do revolution about the y-axis. Take the formula in the yellow box and swap every x and y. We get integral from c to d, 2 pi x, square root of 1 plus dx dy squared dy. Every x is replaced by a y, and every y is replaced by an x. And again, this only works as long as dx dy is continuous. For example, the line segment x is equal to 1 minus y for y between 0 and 1 is revolved about the y-axis to generate the cone shown above. Find its surface area. So it's just preparing everything we need, and then it's using the formula in the yellow box. We're told x is 1 minus y, so dx dy is minus 1. 1 plus dx dy squared is equal to 2. So our formula is surface area is the integral from 0 to 1 we're told that y is between 0 and 1. 2 pi, 1 minus y, root 2 dy is equal to dot, dot, dot. And let's finish with a summary. We've looked at 6 formulae today. We started by talking about volumes by cross sections. Find the formula for the cross-sectional area A and then integrate it. The disk method, same idea, but our cross sections are always circles, so always integrating pi r squared. The washer method was a little bit more complicated. The integral of pi and then bigger radius squared minus smallest radius squared. I spent a lot of today's lesson talking about the shell method. Integral of 2 pi, shell radius, shell height, dx. Those questions are easy as long as you can draw your capital H on your picture and find the shell radius and the shell height. And then after the break, we've done arc length and surfaces of revolution, which is the final 2 formulae here. And for each one of these, we've also done revolution about an axis of revolution which was rotated 90 degrees. And if we rotate it 90 degrees, you have to swap every x and y. If you look on page 4 of midterm 1, you see these formulae, or at least most of these formulae are there in this form. You'll be given exactly the same formulae in midterm 2. And that is the end of this week's lesson. We have 2 lectures left to cover chapter 7. Next lesson, I'm going to talk about inverse functions and their derivatives, natural logarithms, and exponential functions. Are there any questions? I can't remember the average. You can see the average in my grades section. I don't know what is happening with my lab today. I don't know if it's a problem with Blackboard's latest update. I don't know if it's a problem with Pearson's system.